Continuing with our discussion of graphs for scale data, I'm going to cover the box plot and the scatter plot in this video. Now the box plot is a useful plot because, again, it does kind of what the histogram allows us to do, which is to look at the overall shape of a distribution and to assess that distribution for central tendency, for skew and so on. But it does it. The box plot is constructed using slightly different figures. So the center line of the box plot here represents the median, or the value of the 50th percentile. And we talked about this concept in previous videos of percentiles. And the value of the median is calculated by, if you can imagine, lining up, in this case, every country in a row in ascending order according to its score on Gini income inequality. Gini is a measure which varies from 0 to 100 or 0 to 1. And you line them up in order from lowest to highest, then the value which falls in the middle of that set. So the example we looked at was where we had a row of, I think it was 21 observations, and that the middle observation, whatever that score was, would be our median value. And the shaded region of a box plot then is defined by two other figures, which are the value of the 75th percentile and the 25th percentile. So if you can imagine that concept again of arranging the cases in rank order, the value of the 25th percentile simply is 25% of the way over, or again, if you can imagine, halfway between the median and the minimum. And the 75th percentile then is the score on the case that falls halfway between our median value and our maximum value. If you remember if you did study Leaving Cert Maths, you would have come across this concept as the interquartile range, and this is the range that's used to construct any box plot. So every box plot we come across is constructed using these same conditions in Stata, at least. Now there's a couple of other things which are useful about a box plot, is that with a small data set like this, and again this is using country level data, it allows us to identify outliers. So these are cases with extreme values. And the way that these are identified is you'll see them as dots either falling to the top of the graph if they represent extremely high values, or to the bottom of the graph if they represent extremely low values. And the way Stata decides whether or not to identify these specific points is if they fall 1.5 times the interquartile range, which is this distance here. If any score, if any point, whether it's an individual or a country, falls greater than 1.5 times this distance here, then it is marked on the plot as an outlier, and similarly below for low values. So if you can imagine as well, it's sort of like looking down on top of a histogram. It allows us to look and see where the concentration of cases is, but more importantly, it allows us to assess central tendency. Is the median representative of a typical score, or are those scores spread out quite widely, or are they narrowly concentrated? We'll do an example in a moment looking at income. Useful thing about box plots is their visual parsimony. You can divide them up, you can split them by categories of another variable. So here we have an example of household disposable income split by tenure group. So we have a separate box plot for each tenure group. Here's our owners, those who own outright, mortgagers, renters, local authority renters, and those living rent-free. And we can see how the medians differ here by looking at the center line. The highest income is in the mortgage group, the lowest is in the local authority group. And we can also assess the spread of values, or the variability of values around that average. So we see here it's relatively more concentrated for local authority tenants, slightly more widely distributed here for mortgagers, and we've got quite a considerable number of outliers here in the local authority. That's households with a net household disposable income score greater than 1.5 times this distance. So let's have a look at how to do this in Stata. The base command for implementing, or for producing, a box plot is graph box and then the variable name. And we'll see here, we'll just reproduce the previous graph, graph using the same variable previously from the slides, but now just for the whole sample. If we run that, we see we get something that looks a little bit like this, kind of a small concentration of values in the lower range, and a large sort of set of these straggling outliers up here to the top. Now, to put this in perspective, it might be useful to look back at the structure of the histogram to see some of the similarities. So if we remember back to the histogram, we saw that we had quite a narrow concentration of values over towards the left side of that graph, to the left tail of that graph. And we said that this is sort of typical of the income distribution of a country like Ireland, where incomes are sort of concentrated in the lower range, quite closely clustered around the median. But we have a small number of outliers here, just barely visible because of the way the bins are calibrated. Out here in the tails, a couple of houses with an income above 800 and a couple more with an income above 1 million. Similarly, if we run the box plot, we see again that our median value is represented here. If we were modifying this, we might want to label the axis to make it a bit more legible, maybe to get a greater sense of where that value is falling. We can also get the exact median by running summary statistics. So we see here there's quite a narrow concentration of values around the median. So we could perhaps conclude from this that given the low variability around here, that the median is representative of a typical household income. But then we have this problem as well, which is the fact that we've got all these, quite a considerable number of outlier cases. And as we saw in our session on summary statistics, the effect of the presence of a large number of significant outliers is it tends to inflate our summary statistics. Now, the median is robust to that, but we know that the mean isn't. But again, it is something we need to think about, and later this will become quite important when we think about how we model and how we analyze further the relationship between other variables and household income. The shape of that distribution is quite important in determining the types of statistical analysis we apply to it. As I said, box plots work quite well when split over categories of another variable. So to reproduce the graph that we saw on the slide using the slightly newer 2019 silk data, we simply add to this the option over and then our variable, which is HH021. So to produce that split box plot, we need our original variable, which we used up here, which is the household disposable income. And we need to add to that this little option, which is over, and the variable that we want to split it over. And then we've got a little bit of code here just to apply labels and to angle those labels at 45 degrees. It's because we want to know what each of the categories is. When we run that, we get something that looks similar to the previous. Again, we could rotate this if we wanted. But we see here we've got an indication of where the median incomes fall and how they vary. And as with the 2015 data, we see that the highest incomes are among mortgagers. Again, part of the effect of the difference here relative to this is we've got a lot of retired individuals in the outright owner category who might own their properties but might also have lower incomes. So part of this is kind of a life course or a life stage effect. Rental tenant market rent tenants then, slightly lower incomes again, somewhat on a par with the outright owners, and the lowest we see are amongst those living in reduced rent accommodation or living rent free. So again, we could rotate that graph sideways if we wanted. We could impose further restrictions to just look at incomes under 200,000, and that might give us a slightly better indication of the variability by expanding out the shaded area. If we were to do that, we see here we get kind of a clearer sense of where those values are falling. And again, if you are applying any settings like that, you need to be explicit about it in your write-up that you did impose that setting and that you did make that exclusion for legibility. The next type of graph we're going to look at is a scatter plot. And a scatter plot is a series of points which are defined by their score on two variables. In this case, we have an horizontal x-axis variable, which is union density. Again, this is country level data, so each of these data points represents a country depending on the type of data. If you're working with the EU Silk, then each one of these data points will represent an individual or a household. In this case, it's country level data. And we have a y-axis, a vertical axis, which is the Gini coefficient. Again, our income inequality score that varies on this scale from 0 to 100. So the position of this country here is defined by its score on union density on X and its inequality score on Y. The points are identified, as we say here, by both scores. And generally speaking, the orientation of these graphs is important. If we're setting these up to explore hypotheses or to look at specific relationships or associations, you always want to make sure that you position the dependent variable on the y-axis and the independent on the x-axis. So in this, we're assessing the relationship between union density and inequality. We're suggesting that, or the direction of our hypothesis, if you like, is that union density has some effect on inequality. That more highly unionized countries tend to be more tend to be less unequal. So we see here somewhat substantiated this sort of falling rate of inequality as we look across into the higher bands of union density. Again, we'll look at how to characterize this more formally when we get to looking at correlation and regression. What you will commonly see in these graphs is a fit line or a regression line. Depending on the text you're reading, it's referred to by multiple names: regression line, resistant line, slope line, which shows the direction of the association. We will kind of look more formally at the properties of these lines and how they're calculated using ordinary least squares later on in the course. But for the moment, it allows us to assess the direction and the strength of the relationship by looking at sort of the incline of the slope and the direction of the slope. This is an example from Wilkinson and Pickett, the relationship between income inequality and life expectancy. So in their book, they suggest that inequality is associated with life expectancy, but it's negatively associated. So higher income inequality, lower life expectancy. And we see that somewhat substantiated here. Again, as I mentioned in class, there's quite a lot of research in this area. It's quite a contested notion, so it's worth bearing that in mind, but it is quite a classical example that you see time and again. One of the analyses they perform in their book as well is to look at the relationship between women's status, and to this we add another indicator, which is child well-being. These are both standardized indices built using, I think it's 3 questions on each, and they find a positive association. So we see here, as women's status increases, as the scores on women's status increase, so too do the scores increase in child well-being. Again, we're kind of phrasing this as a causal relationship, even though in reality it's not, but sometimes that language is easier for you when you're trying to get a handle on the concepts. It's by no means a straightforward relationship. As we can see here, the points are quite widely distributed, but nonetheless it does give us an early indication that there might be something going on that's worth exploring. And then finally, we can implement what's called a scatterplot matrix. Scatterplot matrix is simply a scatterplot that's constructed using more than 2 variables. And why this is useful is it allows us to give a quick visual inspection to multiple correlations or any combination we want by reading off both vertically and horizontally from the variable names. So the cell at which 2 variables intersect is the scatterplot for that pair of variables. What that means is if we want to look at the scatterplot for inequality and trade, we simply measure up from trade, across from inequality. So this axis here is the inequality axis, and this one here is the trade axis. And it allows us to look at the slightly negative relationship between those two. We move across to this one. We also see it's quite common to use the half option in these to turn off the top half or to make it slightly more legible. So we see this one repeated here, trade in goods and services. And Gini, same one down here. So these are just kind of mirrors of each other. If we wanted to look at, and again, we can do this with any combination, not just with the outcome variable. We could look at the relationship between trade and health expenditure by looking at this plot, or the relationship between FDI and trade by reading across and up to this cell here. So for a practical example, I'm just going to switch data quickly to a country level data set. And again, the basic graph command is given by graph two-way scatter, or the shorter version, which is scatter. Now, as I mentioned earlier in the slideshow, the positioning of the order of the variables in this command is quite important. We'll talk a little bit more later in the course about hypotheses, but the way your hypothesis is phrased, you want to make sure that you get the positioning or the placement of the dependent variable right. So if we see the way this is set up, the variable that appears first in the command line here is the one that's going to appear on the vertical axis. If I was to reverse those, the order of those variables, then health expenditure would be on Y and Gini would be down here in the end. You can still read the direction of the correlation. It's just kind of convention, and it's a little bit more intuitive to read it with the dependent variable on the Y. So in this case, we're hypothesizing that health expenditure is related to the Gini coefficient, and the direction we're suggesting is that countries with higher health expenditure may tend to have lower levels of inequality. And again, there's no real necessarily intuitive or theoretical reason we might suggest this. It's just for illustration. And we can see here that there appears to be possibly a modest negative correlation between these two. That as we ascend the axis or the scale of health expenditure, we see that coincides with lower levels of income inequality. The scatterplot matrix then is is generated by simply typing graph matrix and as many variable names as we want to include, but I'll suggest as many as is visually appropriate. The more variables that we add to this, the less legible the plots become, because the cells become smaller and smaller. So as you can see here, when we run this, we get a graph that looks like this. We've got our 5 variables included here. And again, using the same convention, we can read across and up. If we want to look at the correlation between health spending and union density, we read over from this one, up from this one, it's this cell here. If we want to look at the correlation between union density and Gini, we move over and up, it's this cell here. And again, we can do this with any combination of variables we wish. Health spend and trade is this one. Gross national income and trade is this one here. Again, there are a few settings we can add to that to make it a bit more legible. If we add the option half, then Stata will turn off or will exclude those plots in the top and the top half to the right of the variable names, and you can just read it off from this side. Makes it a little bit easier to read across and to interpret. Going back to the first example then, and as we saw in the slides, we often use fit lines or resistant lines to characterize the relationship between two interval or ratio variables. So taking the example of the plot between health expenditure and inequality, we see here that to implement this, we need first of all graph two-way, and then in brackets we have our scatterplot command, which is the same as this one, scatter health x GDP Gini, and then lfit, which is linear fit, shorthand for linear fit, health expenditure over GDP and Gini. And if we run this all together, again, remember it's important that you highlight the command in its entirety and run this, we get a plot that looks like this. Now we need to add some additional settings to this, as we looked at in class. You would need to label the variables, label the axis, put a title on it so we can identify what the measures are. But we can see here again the sort of negative direction of travel, this negative relationship between Gini and health, which is suggesting to us, again, lower levels of inequality are associated with higher levels of health expenditure and vice versa. You'll remember I talked about the orientation here, which is quite important. And if you notice, the orientation in the command here is reversed. So if we switch that around so that our Gini is now on the vertical axis, it makes that a little bit more legible if we rerun the command. So we see here again, both of those directions sort of make sense. The causal direction isn't really that clear. Just to be consistent, again, we see here, just to prove that, again, it doesn't alter, while it doesn't alter the direction of the line, it does make it a little bit less intuitive to interpret if the orientation of the variables isn't consistent with the way you've hypothesized the relationship. And then finally, if you want to add some annotations to this, there's a range of different options and settings you can use. You can title your axes by using the subcommand ytitle. So again, you could give the variable name. You can title the x-axis by using the x title and then brackets and inverted commas. And the graph syntax for titling is common to most of the graph types that we've looked at so far, which is title in brackets, note in brackets, and subtitle in brackets. And if you add those all together, you get something that looks a little bit neater. You've got proper labeling on the axis. You've got the variable and the units identified, the data source, and what it's measuring. And you can add, you can alter these any which way you want. You probably, if you wanted to add in the date of the data, you could, type it in there and it'll simply appear. Now I mentioned that saving these graphs before is quite important. You want to make sure that if you want to use these in any of the conventional word editors, that you want to save them as a compatible graph type. So let's say you've generated your graph and you want to save it. All you do is right click anywhere within the graph, click Save As, and then go down here to Save as File Type, and then save it as either a TIFF, a TIFF, or a PNG, Portable Network Graphic. These two are probably most readily readable into most word processors. So I suggest you use those ones. There's not a huge amount of loss with those ones as well, in terms of resolution, certainly for the types of graph that we'll be doing in the course. So that is how to implement boxplots and scatterplots in Stata.